Okay, then if not, just want to point out that today we will open another quiz. So we have already since last Monday the first quiz running for assignment one, from machine learning to federated learning. And this quiz tests your understanding of the concepts from the lecture and your solution to the coding assignment. So before you start to take the quiz, I highly recommend that you read the lecture notes or the slides, which you can find here on the My Courses page and also on our GitHub repository. So you can find the slides from lecture one, and you can also find there the specification for the coding part of the assignment. So there was a question, what's the time limit, the submission deadline? As indicated in the first lecture, we have around 2 weeks. You have around 2 weeks until you submit the solutions or you answer the quizzes. So there was a small typo actually in the slides regarding the days or the name of the days for the deadlines. So you will find here in the slides, I will not scroll down here. In schedule, you will find the deadlines. So the deadline for the first quiz is the 8th of March. So this is Sunday next week. You have 2 weeks, 2 weeks for the first assignment, and the same deadline applies to assignment two. So also assignment two will be due at the end of Sunday, the 8th of March. So we have two assignments due for the same deadline. This should give you some flexibility in scheduling your work time. On average, you have to complete one quiz per week during the first part of the course. As a reminder, this course consists of two parts. The first part is now in February and March, consisting of 8 lectures with 8 assignments and 8 quizzes. And the second part, then in April and May, is the course project, where you find already some information here on the My Courses page. But as I mentioned, we will have a dedicated project kickoff event in the beginning of April. So more details about the project will come at a later point. Okay, so that's about the organization. Let me now start with the course topic today, which is maybe the main idea of the whole course, which I call a federated learning design principle. And yeah, we will see today what I mean by this design principle and how we can use it. So a design principle is something that allows us in a principled way to design something, to design federated learning algorithms or systems. Okay, full screen mode. Let's go. So to remind you from last lecture, we stopped at or we introduced a federated learning network as a mathematical model, a mathematical structure for representing federated learning systems. So federated learning system can be very complicated, consist of many different devices, and we need to abstract away the details in order to make some progress or in order to have any chance at the theoretical or formal analysis of the federated learning network. And for example, then to study if this federated learning network is robust or if it protects the privacy to a satisfying degree. In order to do all these things, we need to throw away a lot of details. So we need to abstract away all the nitty-gritty details, and we ended up with a graph structure where the nodes of the graph represent devices, and each device, which could be a smartphone, could be a laptop, could be a supercomputer, uh, they train a machine learning model. So each device wants to train a machine learning model, which is here denoted by calligraphic H. In this course and in general, when I say machine learning model, then I mean a set of functions or a hypothesis space. So I want to remind you again about the terminology, which is explained in our dictionary, in this Alto Dictionary of Machine Learning, and we still have plenty of soft cover copies available. So if you want to get a nice physical piece or copy of this dictionary, let me know. We still have plenty in stock. So at each node or device, we want to train a model, and we train this model by minimizing a loss function. So we also have a loss function at each node. And in principle, you can have arbitrary loss functions and models at different nodes. So some node can carry a decision tree, another node can carry a linear regression model. And some of these nodes, which represent devices, are connected by an edge. And these edges, they are weighted. We assign a non-negative weight to an edge. And this weight indicates how much do these two nodes collaborate with each other. And today we will see how we can make this happen actually. So how can we make them collaborate? Yeah, again, first of all, why do we want to take all this kind of why are we dealing with all this complicated collaboration stuff, and why not just training models? Each node trains its own model. Well, in practice, or in many applications, we have too little data. So each one of us, I guess, would like a nice healthcare app, which provides a tailored diet that maximizes your well-being. And to train such a complicated model, so this typically requires a high dimensional model, we need a lot of training data. And I, for example, don't have enough training data. So I would need to collaborate with others who also have a bit of training data to share information and then train a more powerful model. So I have illustrated this here with a simple linear regression model. When you have a linear regression model with using D features, D for dimension, then you would need roughly the same number of data points. And the dimension of modern models, so you can roughly estimate the dimension of a deep neural network, or the model represented by a deep neural network, by the number of parameters. And these modern models have 100 billions of parameters, which means you would need 100 billions of training data points. And one person alone typically doesn't have such many training data points, but a collection or a population of, let's say, all European citizens, roughly 500 people, if they pool together their data points, you get maybe a more reasonable amount of training data for training highly nonlinear models. And we want to do this in a distributed fashion. So we don't want to share all our local data sets with some central entity, but we want to do this sharing information in a distributed fashion by only sharing what's really necessary, what's needed to train the models. And today, this design principle that I will talk about can do this in useful settings. Okay, and how do we do it? Well, the idea is we use regularization techniques. So if you remember from the first lecture, where I gave a quick review of basic machine learning, and regularization is, I would say, the key tool for practical machine learning. Practical machine learning can be either is trial and error, and this trial and error you can do either by trying out different models, training them, computing the validation error, and then trying out a new model based on the validation results. Or you do it in a more smooth way, so to say, or a continuous way by tuning regularization parameters. And these regularization parameters, they control, for example, how we augment data points. In most machine learning applications, the data points have some intrinsic symmetries, or let's say the machine learning problem has some intrinsic symmetries. Like prime example is when you want to detect cat images, then you can immediately replace any cat image that you have in your training data set with a rotated cat image, or you can replace a cat image with a shifted version of a cat image. So there are often many symmetries that you can exploit for adding additional data points or for augmenting the training data set. Yet another form of regularization is to prune the local models or to make the machine learning model smaller. How can you make a machine learning model smaller? Well, for example, in a linear model, you use fewer features, or in a deep neural network, you kick out layers. You prune, and this is literally pruning a deep neural network by removing neurons or entire layers. That's how you make a model smaller. And this is one way to regularize a model. And the third, almost equivalent form. So these three forms, they are like different perspectives on the same technique. Is adding a penalty term. So instead of augmenting the data or making the model smaller, you add an additional term to the loss function. Okay, and I want to illustrate how we do this, how we do regularization in federated learning first via this augmentation, data augmentation, and then show you how it naturally is equivalent to adding a penalty term to a loss function. So I have tried to explain this already in the first lecture, but I didn't give a good I didn't use a nice figure that I now have here. So we have this blue data set. This is one device. This is node I, and then another device I prime. So this might be another user or another device or smartphone that has some local data points. And here we have also blue local data points. So this blue node trains a linear model, and this red node trains a linear model. So how can we make them collaborate with each other? Well, we could use their predictions on a test set that I denote by calligraphic D, I prime. By using the predictions on this test set as pseudo labels. So we can use then the labels obtained from the red predictor on this test set as additional data points for the blue node, and the predictions of the blue curve, of the blue straight line here, that we get the predictions here on this training set, test set, we use for augmenting the red data set. So it seems a very natural idea. And this is the core idea, maybe one of the few core ideas of the whole course. So it would be useful if you try to really understand what's going on here, and ask questions now. So is there any question at this point? We had in the first lecture already some questions regarding how do we build this test set and how do we build it in a privacy friendly way. So one way to build this test set here is just we agree on a randomly generated test set that is shared by some global entity, by some administrator of the federated learning system, who tells each participating node, hey, here we use this test data set. Or a more distributed way is like in a peer-to-peer network. These two nodes discover each other, and they say, let's agree on a test set, like this node gives 10% of its data points and this red node gives 10% of their data points, and they put it together and get a training set. There's a question, is there a hierarchy to decide in which order to train the local models? No, there will be no natural hierarchy. You can introduce a hierarchy, but it doesn't come out naturally in the design principle that I will present today. So there's no hierarchy. Then another question, each model is trained once and then fine-tuned on the new data set or trained from scratch. Yeah, so this will turn out to be an iterative process. So in each iteration, they use the prediction on this common test set to adapt a bit, to update the local data sets. So it's more like fine-tuning. It's not training from scratch. So the nodes they remember, they have a memory, so they they adapt their current model parameters based on the predictions on this test set. Yeah, one before I take the next question regarding this hierarchy. Actually, now when I think about it, you can bring in a hierarchy in terms of the network structure. So you could build the federated learning network or the edge set could represent or reflect some hierarchy. So there are ways to construct hierarchical networks. But that's a very good comment, actually. I tried to tell a bit more about this, how to design different network structures, in particular hierarchical network models at the later lecture. Yes, so next comment. So both devices use the test data set and then take the points from the other device for training. To clarify, so for example, this blue node here uses uses the predictions of this red model on the test set as the labels for this test set. So this blue node augments its local data set by the data points in this test set, but using the predictions of the red model as the labels in this test data set. So this blue node does not use the red local data set itself. It indirectly uses the information in this red data points by using the predictions of this red model. And this red model has picked up to some extent the information in this red data sets. Okay. And yeah, if you write down these ideas, so you could measure also uh, or you can measure then the discrepancy between node I and I prime. So let's say we want to minimize this discrepancy. We want to this if these models collaborate, then we could just penalize the discrepancy. And how do we measure the discrepancy between two models? Well, we compare the predictions on the test set. So we just take the squared difference of the predictions for each data point in the test set. That's how we can compare models. And what I like about this approach is we didn't make any assumptions about the structure of the models. So this could be, I have used here parametric models because I've indicated here model parameters, but we can compute this discrepancy measure for any model. So this hypothesis maps here could come from a decision tree. So this quantity here, this summing the square differences, you can also do for decision trees. That's how you could couple decision trees. And there's not much work on federated learning for decision trees. But this idea here uh, natively supports decision trees. Then there's a question, how do you make sure that the local models are not making each other worse by giving bad predictions? Yes, that's a very good point. So the question is, why should two nodes collaborate if they are very different? So if this blue data set would have a very different underlying statistic than the red data set. So this is true. So if you should not make them collaborate. But in this course, we assume somebody has given us already the hint which nodes should collaborate. And also, there are many federated learning applications where we say already from the start, we want to train one single model that is used by all nodes. In particular, in server-based federated learning, you train one global model that is used by all nodes. So for such applications, we want to all devices to collaborate and to get the same model in the end. But as this question already pointed out, this might not be useful if some nodes have very different data distribution, then you should not do it. And this is related to data heterogeneity or non-IID settings. And for this, you should, so in such cases, you should beforehand find out should you collaborate or not. And I mentioned already in the first lecture some ideas how you could do this. So does anyone have an idea how to find out if two nodes should collaborate? What could they do? What could these devices do to find out if they should collaborate? Yeah, there was a question. Could you give an example of a scenario where two nodes should not collaborate? Yeah, as I said, when these two nodes, they measure data with very different distributions. So let's say you have one node, which is a weather sensor, which reads in every minute temperatures, which is placed, for example, in the north of Finland. And then you have another weather station placed in the south of Spain. Then the data that they observe or the data generation process might have a very different distribution, and you should maybe learn different models. One weather forecast model in for Finland and one weather forecast model for Spain. You should not force them to be identical models. Yeah, one way to decide, or one idea would be just compute simple statistics of the data set. What could be a simple statistic like the mean, the sample mean, and the sample variance, and then compare those two. So if they have very different parameters or statistical parameters, then you do not let them collaborate. But we will see our design principle is quite robust, so it can tolerate a few uh, counterproductive collaborations between pairs, as long as each node collaborates with sufficiently many useful partners, so which have the same distribution. Yeah, then regarding my example of Finnish and Spanish weather forecast, there's another comment or question. Why should the Spain and Finland weather statistics be part of the same federated learning network? Yeah, it might be the case that they should not be part of the same federated learning network. But on the other hand, there might be still some basic statistical pattern present in the Spanish data that could still be useful also for the Finnish data, for the Finnish weather forecast. Let's say some long-term effects or long-range effects, like I mean, not for Finland, but I know from my childhood, I was very eager that the first snow comes, and then you have the probability or the chance that you get snow in Austria depends often on the weather behavior in like Italy or around Italy area. And also there are these uh, high pressure periods where they are related to the condition, the atmospheric condition at some islands in the Atlantic. If I remember correctly, they are Azoren hoch in German. Uh, I don't know the correct English translation. So there could be relevant information in this case in the Spanish weather data for Finnish data for Finnish weather forecasts. Um, yeah, so if we write down this discrepancy measure, uh, and now if we assume these are like linear models, so in particular parametric models, then you end up with this cute expression here. So you can write this discrepancy measure actually as a quadratic form in terms of the differences between model parameters. And this leads us to some widely used discrepancy measures. So we can compare parametric models in a federated learning network by comparing or by looking at the difference between their model parameters. So the model parameters at connected nodes I and I prime should be small. And then we need some measure of small, and this is something in mathematics called like a norm, or something that increases with the norm, or norm-like function. So I have shown here some examples that have been studied in the literature, like the squared Euclidean norm is widely used and will also be used in many examples in this course for its nice convexity properties. You can also use a quadratic form using some matrix, some fixed matrix, and this matrix Q here, for example, if we compare this with the previous slide, this matrix Q is made up of the feature vectors in this test set. So this test set, how you augment the data sets, is directly translated into the shape of the penalty function that we add to the loss functions. Then other choices are the one norm or some generic norm. Okay, but this is only one example. In particular, this type of discrepancy measures, or this family of discrepancy measures, can only be used for parametric models. And we can also build or craft discrepancy measures for clustering applications. So we are now recently started to work on clustering applications, and we can use also the KL or Kalbeck-Leibler divergence between the distributions or this Gaussian mixture models that are parametrized by some vector to measure the discrepancy. And using this discrepancy measure results then in federated soft clustering. So you will hear then in lecture 5 next week about federated learning methods for clustering. Okay, I think I have here the wrong, an outdated slide set, so just give me a second. And I suggest you use the short break to think about questions and post them on the chat. Okay, so I was just telling about these different discrepancy measures, and there's a lot of design freedom. So you can craft whatever discrepancy measure you like, and some of them are more useful, some of them are less useful. And we have recently started to look at a specific choice for this discrepancy measure, which is useful for federated k-means. So choosing the right discrepancy measure gives you a federated k-means method. By plugging in this discrepancy measure that you see here on this slide into our design principle, which I will soon finally present to you. And here in this discrepancy measure, we compare the cluster centroids in a k-means method. So in k-means, in federated k-means, each node tries to cluster its local data set. So this blue node tries to cluster, let's say, into two clusters, and this red node tries to cluster into two clusters. And in federated k-means, we want those nodes to end up with the same cluster means. So instead of pooling together all these local data sets, which could be patient records, which is sensitive data, and then apply a clustering analysis, we want to do this clustering analysis in a distributed and privacy friendly way. And using this design principle with this type of discrepancy measure allows you to do this. And you will hear more about this in greater detail in lecture 5 on federated clustering next week. Or no, it's actually 2 weeks, 2 weeks from now. Okay, so now that I have tried to convince you about adding a discrepancy or why we should use discrepancy measures to couple local model training. How do we combine them over the edges? And one straightforward way is, well, we just sum them up. So if we want to couple all the devices that are connected via an edge in the federated learning network, then we should take into account all the discrepancy measures over all edges. And that's why we add them up over all edges. So this sum here goes over all edges in the federated learning network. And for each edge, we multiply the discrepancy measure by the edge weight. So the edge weight amplifies or de-emphasizes the discrepancies over certain edges. So this allows us to put more emphasis on certain collaborations, like for example, between this blue and red node, we might not want so much collaboration, so we make this rather small. Whereas in this cluster or this tight-knit subset of nodes, we want a lot of collaboration, so we choose a large edge weight. Okay, and here it is. Here's the design principle, which is now a pretty much small step now that we have introduced all the building blocks. So we have here the local loss at each node. Each node tries to train a local model. So the first node tries to train a local model calligraphic H1 until the last node, the N for the number of nodes. N is the number of nodes in the network. Uh, Tries to train a model calligraphic age n. And what couples those individual machine learning trainings is this penalty or this regularization term here. So this regularization term here is the generalized total variation. Hence, this whole thing is called generalized total variation minimization or GTV min. And this is the core formulation of federated learning in this course. Everything we do in this course is following the same workflow. So you have a federated learning application in mind or at hand. First thing is you try to formulate or model it using a GTV min instance. You have a lot of design freedom here. So what are the local models? You can choose different local models. You can choose different loss functions at each node. And you can choose different edges, edge sets and edge weights. You can also scale this GTV term, GTV term globally by this alpha. This is the regularization strength parameter. So the first step also in the project is formulate your application as a GTV min problem. This is an optimization problem. So we start off from an optimization problem formulation. And this is a similar approach or similar workflow as in basic machine learning. In basic machine learning, we formulate machine learning as empirical risk minimization or a model training problem. This is again an optimization problem. And here we have a bit more structured optimization problem. So we have this additional GTV term. This is actually a form of regularization, adding a penalty term to the loss functions. But it's also a bit more structured hypothesis space. So you could interpret this training the local models as training a compound model, which consists of H1 till Hn as its components. So you could think of this GTV min as a specific type of regularized model training, where the model consists of different local models, which can be different, potentially different, and very different, by the way. So one of these local models can be a decision tree. Another local model can be a large language model or a transformer network. in particular, and yet another model could be another local linear model could be a linear model. So this GTV-min formulation allows for very heterogeneous federated learning systems. We can model very different federated learning systems, which makes it quite flexible. Also, the loss function, the choice of loss function, gives a lot of flexibility. This loss function could be obtained for some nodes by a reward signal. And this is relevant for federated reinforcement learning. So in federated reinforcement learning problems, you do not have typically the opportunity to compute the training error because you don't know what the correct labels are. You only know, let's say you want to predict the steering angle of a self-driving car, and you only know if it was useful or not. That is, did it crash into something or not? And based on this feedback, using some collision sensor, you can construct the loss function. There's a comment here or question. So is GTV-min like a centralized loss function for the whole federated learning network? Yes, you can interpret this objective function as a very complicated global loss function for a big model training problem. And this model consists of components. So it's in mathematical terms, you could think of it as a product space. So it's not a simple hypothesis space, but it's a product space with components being the individual local models or local hypothesis spaces. So there's a lot of beautiful structure in here. And there's also a discrete structure coming in via this sum over all edges. So we will see that the properties of this GTV-min depends crucially on the structure of the federated learning network or on the graph structure that it has. And for this, to characterize the graph structure, we will use the Laplacian matrix of this federated learning network, and in particular, its eigenvalues. Okay, let's look at some extreme cases. It's always good to get some feel for such an optimization problem by looking at special cases. So for alpha, if we set alpha equal to 0, then GTV-min splits into independent model training, into independent empirical risk minimization for each node. So we cover the case of independent model training at each node as a special case for alpha equals 0. And roughly speaking, the smaller we choose alpha, the less collaboration will there be. At the other extreme, if we choose alpha larger and larger and beyond a certain threshold value, then we will enforce that each node ends up with the same model. So we couple the model training so strong, the coupling is so strong that there cannot be two nodes with fundamentally different models in the end. So this other extreme case corresponds to the most widely used setting of federated learning, where you have one server which maintains or which trains a global model, and this global model training is supported by client workers. And we can do this equivalently in a fully distributed way by using GTV-min with a sufficiently large value of alpha. Just to point out, we will see next week in the federated learning algorithms lectures how to solve this GTV-min problem by distributed optimization. So there is no need for a server update and a broadcast to clients. This is fully distributed based on message passing, like in a peer-to-peer network. But still, we can end up with the same, like in the server setting, with a single global model. It's just that each node holds a copy of this global model. And we can enforce this by choosing alpha sufficiently large. And then there's an intermediate range, which is the more interesting case. And in this intermediate range of values for alpha, this GTV-min basically does a separate global model for each cluster. And this depends. So this GTV-min, when you solve GTV-min, you adaptively or you automatically choose the nodes that belong together based on the edges. So if you have nodes that are connected via many edges, so there's a good connectivity. And for this, to characterize the connectivity, you can use the eigenvalues of the Laplacian matrix. And for those nodes which are well connected, GTV-min solutions, they are almost identical. So GTV-min will, if you solve GTV-min, you will end up with copies of the same model at these red nodes and copies of the same, almost the same model at the blue nodes. And the same goes for the green nodes. So this GTV-min automatically adapts to the connectivity structure of the federated learning network. But for this to work well, you need to make the structure useful. So you need to make sure that you only put edges and edges with high weight between nodes that you expect they should collaborate. In some applications, you don't have much choice. You say, I'm here alone with my smartphone. I have a very small data set and I just can connect with this other device. So there's not much else you can do. You need to put an edge there. Otherwise, you stay alone. So in some applications, there is not much of a choice, but in other applications, you can design the network to some extent. And when you can design the network or learn the network, you should use the statistical properties of the local data sets to decide where to put an edge. Okay, so now that I've introduced GTV-min, discussed the extreme cases, let's look at some special case for parametric models. So I want to remind you that in full generality, GTV-min is an optimization problem over function spaces, or more precisely, over a tuple of function spaces or a Cartesian product of function spaces, which is a very high, can be very high dimensional or very complicated. So to drill down the complexity, it's useful to look at parametric models which are characterized by a parameter vector. In particular, we look at the special case where each node has the same parameter space, so the same number of parameters. And this could be restrictive. So in a federated learning, in many federated learning applications, you might have some nodes having a bigger network, a bigger artificial neural network, and other nodes having a smaller artificial neural network. Then this doesn't work here anymore. So you cannot use this instance of GTV-min. You would need a GTV-min with different dimensions for each node. But this is easily covered in this more general setting. So you can have one hypothesis space being a LLM or a transformer network with 1 trillion parameters. And this model here for node n could be a small multi-layer perceptron with 1,000 parameters or dimension 1,000. So you can easily cover this such an application with this formulation. But this formulation here with equal model dimension is useful for analysis. So we can do a bit more. We can tell a bit more about such special cases, but of course the applicability is limited. Yeah, so if we make this even more specific, we can also look at the discrepancy measure being the squared Euclidean norm. And then GTV-min looks like this. So this is GTV-min for training local linear regression models or local linear models using squared error loss and using the squared Euclidean norm as discrepancy measure. So this is the special case of a special case of GTV-min, so to say. We looked at the parametric models, in particular linear models, which are trained in particular with the squared error loss, and in particular we use the squared Euclidean norm as the discrepancy measure. Okay, any questions at this point? Should we have a 5-minute break? Yeah, let's have a 5-minute break and be back at 5 past 5. Okay, welcome back. to our lecture on our main design principle for federated learning. So let me now talk about some interpretations of GTV-Min, which I found somewhat interesting and maybe useful for the analysis of federated learning systems. So for these interpretations, I focus on a special case of federated learning using smooth and convex loss functions. So this is a strong restriction, but this is typically made in the analysis of machine learning systems. It's an approximation which can be useful, but can also be too crude. So it can be too far away from the actual federated learning system, which uses non-smooth and non-convex loss functions. But for the sake of analysis, let's assume the local loss functions are smooth and convex. And we use the quadratic Euclidean norm between model parameters as discrepancy measure. We also assume that there exists a solution. So you might, maybe a nice bonus task for you, try to find an example for this GTV-Min special case where there is no solution. So can there be smooth and convex loss functions such that this optimization problem does not have a solution? But for now, we assume that there exists a solution. And it turns out that the solution has a similar structure as the the electrical quantities in an electrical circuit. So we can think of the gradient. So the optimality condition involves the gradient of the loss functions, can be interpreted as a current, as an electric current that is provided or introduced by some electrical power source or voltage source in this case. And this current has to satisfy Kirchhoff's law. So I like this interpretation very much because I studied electrical engineering a long time ago. And there's always this slogan, sometimes you hear in the media, AI is the new electricity. And I find this interpretation here a cute way of making this slogan, AI is the new electricity, more rigorous. So this equivalence is in terms of optimization problems. So you can formulate the circuit analysis problem in electrical circuits as an optimization problem, and you can model AI systems as solving optimization problems. And the solution structure or the structure of the solutions to these optimization problems, they have similar forms. They have to satisfy, for example, something like the Kirchhoff's law of the current law or the voltage law. So there are these two rules in circuit analysis, and you see those two rules are also satisfied in the solutions of GTV-Min. I show here on this slide only one type of rule, this current conservation of currents in an electrical circuit. Okay, then I will skip this for the sake of time. Another interpretation is, as I said, the solutions of GTV-Min, they turn out to be local model parameters that are constant or approximately constant over well-connected subsets of this federated learning network. And this in turn means that the nodes that belong to the same cluster here in the network, they share their local data sets, or they are like coupled together exactly. And this is known as locally weighted learning. So you assign different weights to different data points or different data sets. And in this case, you assign weight 1 to all data points that are in the same well-connected subset of nodes. So GTV-Min generalizes locally weighted learning. Yet another interpretation is that GTV-Min generalizes convex clustering. Some of you might have heard about convex clustering. So there's also a convex way to do clustering. And this is based on the following idea. So for each data point that you have originally, So these data points are denoted here by A superscript 1 is the first data point, A superscript 2 is the second, and here is third data point. You introduce a model parameter, a local model parameter. So we can think of each original data point as a node in a federated learning system. And then you try to find local model parameters that on the one hand are not too far away from their respective data point, but on the other hand uh, uh, agree well or are similar to the other local model parameters. And it turns out if you use for the discrepancy measure here not the squared Euclidean norm, but only the Euclidean norm. So this is an important detail here. We use here the Euclidean norm. We do not use the squared Euclidean norm. And using the norm instead of the squared norm results in these model parameters tending to be exactly identical. So these model parameters, they try to attract each other. They are only hindered by this that because they are required also to stay close to the original data points. And it turns out that many of those local model parameters, they coincide exactly. And for those model parameters that they coincide exactly, you say the corresponding data points belong to the same cluster. Okay, then regarding the properties of the solutions, so what can we say about the solutions of GTV-min? The solutions of GTV-min are local model parameters. So when we solve GTV-min, we end up with trained model parameters. And how can we say if they are useful or not? So can we use the local loss value? In general, it's not enough because to start with, we said that the local data sets are too small, and in turn, the local loss values, they are not really informative enough. So they can be very small, although we didn't learn anything useful, any useful model. So it might be better to average these local losses over all nodes that end up with similar model parameters. Okay, and then which nodes end up with similar model parameters? Well, this depends on the value of alpha. So alpha is the regularization strength that we use in GTV-min. If we choose a very small alpha, as I mentioned before, in the extreme case, alpha almost equals 0, each node trains its own model and ignores everybody else. So here a cluster is the smallest possible cluster, which means only one node. And the larger we make alpha, the larger become the clusters that GTV-min delivers. So the larger alpha, the larger are the clusters in which the local model parameters are almost identical. And then it would be nice to have some guidance how large do we have to make alpha really? So this is very hand wavy now, or very qualitative, this discussion. And can we say something quantitative about which value should we use for alpha such that the deviation of the model parameters in these three nodes, for example, is less than 10%? And you can do this by some analysis. So it turns out you can bound the deviation or the variation of local model parameters by an upper bound that consists of properties of the local loss functions. So this epsilon is a measure of how similar are the local loss function. So you can think of this epsilon as a measure for the homogeneity or heterogeneity on the other hand of the local data sets. So if the local data sets are very homogeneous, so they are sampled from a similar distribution or identical distribution, then this epsilon can be chosen very small. On the other hand, if these local data sets are chosen from very different distributions, then you can satisfy this inequality or this condition only for large values of epsilon. So this epsilon is a measure of heterogeneity in the federated learning network. Okay, and then we also have a parameter that characterizes the connectivity of the federated learning network. And this is this famous lambda 2 that I already mentioned in the previous lecture. So this lambda 2 is the second smallest eigenvalue of the Laplacian matrix that we can define for a federated learning network. So remember from the last lecture, to each undirected graph, we can naturally define we can literally assign a Laplacian matrix. And this Laplacian matrix is positive semi-definite. It's symmetric and positive semi-definite. So it has a spectral decomposition. And in the spectral decomposition appears a sequence of eigenvalues. The first eigenvalue, lambda 1, is always 0. And the second eigenvalue tells us if the graph is connected. So if it's connected, lambda 2 is larger than 0. And the amount of connectivity, so how well it is connected, is reflected by the size or the value of lambda 2. If lambda 2 is very large, then the connectivity is very high. Okay, and we have now an upper bound. One can show this upper bound on the variation of the local model parameters. So this quantity on the left tells us how much do the model parameters in the network vary. So how much are they different in the end? We have solved GTV-min, which gives us local model parameters at each node. And these local model parameters, they deviate a bit from each other. And how much do they deviate? Well, we can upper bound this deviation by this ratio, epsilon, which is a measure for the heterogeneity of the local data set, divided by alpha times lambda 2. So we choosing a sufficiently large alpha such that this quantity is small enough. We enforce that each node learns almost identical model parameters. Okay, any questions at this point? Yeah, I want to again highlight this formula or this analysis here, this upper bound, nicely brings together properties of the local loss functions. So remember, in a federated learning network, we not only have the graph structure. This graph structure is characterized by this lambda 2, the second smallest eigenvalue of the Laplacian matrix, but we also have the local loss functions. So on top of the graph sit local loss functions. And now this bound tells us how these two interact with each other. So when we solve GTV-min, the solutions of GTV-min depend on both on the properties of the local loss functions and on the properties of the federated learning network or the graph, the connectivity structure. And this bound tells us to some degree how they interact. So if we want to have each node ending up with the same model parameters or a copy of the same global model, we must make sure that epsilon is small and or that alpha times lambda 2 is sufficiently large. And depending on the application, we can control only some of these properties. So we typically have control over alpha. Alpha is like a hyperparameter for federated learning algorithms. We might have control over lambda 2 if we can design the network. But in some applications, the network is given. There's just this connectivity available, this wireless connectivity, and it's all you can do. So lambda 2 is basically fixed. And also epsilon might mainly depend on the data that you observe. So you cannot control the data. If you could control the data that you observe, you're not doing machine learning anymore, in a sense. So in machine learning, we need to be able to cope with data from an unknown distribution. So this epsilon is not really under our control, but we can maybe some estimate the degree of heterogeneity. So we get some value of epsilon. But we cannot really steer it. We cannot make epsilon smaller and smaller in general. Instead, we might choose alpha larger and larger. So this is a hyperparameter we can tune easily in many applications. Okay, so that's about the properties of the solutions. And then the next question is, how do we how do we get these solutions? So how do we compute the solutions of GTV-min? How do we solve GTV-min? And how much resources do we need? How much floating point operations do we need? How much bandwidth do we need in wireless links such that this works within acceptable amount of time? These are all questions related to the computational complexity of GTV-min. Okay, and the general idea of this course is that we turn this GTV-min into an algorithm via fixed point characterizations. So we try to find, for a given GTV-min instance, we try to find a fixed point characterization of its solutions. And one very natural fixed point characterization is given by the following idea. So if you have a solutions for GTV-min, then for sure fixing all these components except one and minimizing this objective function only with respect to node I must result in the same solution again. So this is like a self-consistency condition. If this would not be satisfied, this would mean that this could not be a solution. So if we assume that we have a collection of solutions, of trained models for each node, then each model must be optimal for GTV-min if we fix the other models to the trained models we got there. So this is a very natural self-consistency requirement for optimality. And this, by the way, is a fixed point condition. Does anybody know when this condition, so it turns out that this condition is necessary. Again, it's necessary because if this would not be the case, so if this H hat at node I would not be the solution of this problem, but there would be, which means there would be another choice for the model, which results in an even smaller objective value, then I would need to replace this original trained model at node I with this new one, because I have found one that results in a smaller objective value, which contradicts the assumption that I started from a solution. So this is a very simple argument to have this to end up with this necessary condition for a solution for GTV-min. Does anybody have an idea or some guess when this condition here is also sufficient? So as if you have found model parameters or hypotheses that satisfy this fixed point characterization, then you can be sure that they solve GTV-min. Does anyone have an intuition when this condition is sufficient? Yeah, I let this sink in. This is also a nice optional extra task. So maybe till next lecture, you could think about criteria or under which conditions or requirements on the loss functions and this discrepancy measure is this fixed point characterization also sufficient for the solutions of GTV-min. Okay, but let's be happy now with what we have. So we have a necessary condition, which is a fixed point characterization. So we have some equation that involves an operator, and on the left hand of the operator, so the result of the operator has to be the same as the argument of the operator. If you repeat this condition for each node I, you have an equation where on the left side is the trained models, and on the right hand side is an operator that consists of all these node-wise operators applied to the trained models. So this is a fixed point characterization. And you find more about fixed point characterization, by the way, in our Aalto Dictionary of Machine Learning. And once we have such a fixed point characterization, it's very natural to use this operator that shows up in this fixed point characterization to iterate, to generate an iteration. So you start with an initial choice of model parameters here. So I now switched again to a special case of parametric models here. So this is GTV-min for parametric models and using the squared Euclidean norm for the discrepancy measure. And then you can come up with a fixed point characterization, which is something called zero gradient condition, because if these loss functions are also assumed to be smooth and convex, this whole thing, this whole objective function is a smooth and convex objective function. So an optimum is characterized by a zero gradient condition, and the zero gradient condition can be written as a fixed point equation using this operator, f, calligraphic F, superscript eta. And it turns out this characterization is valid for any choice of eta, for any non-zero, in particular for any positive, strictly positive choice of eta. You can build this operator here. So this operator is defined here by this equation. And this operator defines a fixed point characterization for the solutions of GTV-min. So this is the second step in our workflow. Again, the first step in our federated learning workflow is formulate your federated learning application as GTV-min. The next step is characterize the solutions of GTV-min using a fixed point equation. So try to find an operator, calligraphic F here, such that any solution to GTV-min is a fixed point of this operator. And this is straightforward for smooth and convex objective functions, because it's the gradient condition, the zero gradient condition almost directly gives you such an operator. And this operator, you can call it a gradient step operator. This operator consists of take the argument. So when you apply this operator to some local model parameters u at each node, you take the current model parameters and then subtract eta, so this is the learning rate or step size, times the gradient of the objective function. So the gradient step operator is a very natural or canonical choice for this operator in a fixed point characterization, if you have a smooth and convex objective function. We will see next week in lecture 3 that there are also other choices. So this is not the only way, this is not the only construction for an operator f, such that any solution of GTV-min is a fixed point of this operator. There is also another construction that you will hear about in the next lecture, which is called proximal operators. Okay, so once we have succeeded in the second step, so we have found an operator that yields a fixed point characterization of GTV-min. It's quite natural. How do we find a fixed point? And then what we do is we iterate the operator, which is called a fixed point iteration. So how do you find the fixed point of an operator? Well, if you are lucky and this operator has nice properties, in particular, it's what we call a firmly non-expansive operator, or even better, if it's a contractive operator. You will hear more about these notions in next week's lectures. If this operator has nice properties, so it shrinks the difference to the fixed point in every iteration, so to say, then you just repeat the operator. You have an iterative algorithm. Here we have already an iterative algorithm, which is constructed by this operator f. This is the update step that we have to do to take the current model parameters at the current iteration and get better model parameters at the next iteration. So that's the third step in our workflow. We iterate this operator. We do a fixed point iteration. And yeah, for the special case of a smooth and convex objective function, one example of this workflow is gradient descent. So gradient descent is a fixed point iteration when you use this gradient step operator, calligraphic F, eta as the underlying operator. And when does it work? So as I said, this idea of fixed point iteration is nice and good, but this only works if this operator F is nice. So it's something like a contractive operator, or at least non-expansive. And here comes this step size rules that maybe some of you have heard. So when you use gradient methods to train models or to solve optimization problems, you need to be careful with the step size or the learning rate. And in our approach, this learning rate is related to the contraction properties of this operator. So this operator here, this gradient step, is only contractive or only non-expansive if you choose eta sufficiently small. And one way to make it sufficiently small is to make it decaying over a number of iterations. Okay, so this is really important here, this third step of our workflow. So I spent some time on discussing it. So we build federated learning algorithms by running at each node I, we run this fixed point iteration using some operator calligraphic F superscript I. So compared to this example here, to this basic gradient descent operator, in federated learning, we have a different operator for each node I. So we need one operator at each node. These operators are a bit different because these operators reflect the local loss function, the local structure of the federated learning network, like the neighbors and the edge weights to the neighbors. And the operator also depends on the discrepancy measures. So these three components, they define or induce these operators, these fixed point operators in federated learning algorithms. And it's up to you then, to the federated learning engineer, to choose these local loss functions and the federated learning network structure such that these operators become nice in the sense of becoming contractions. Okay. And yeah, what is also interesting that often, or remarkable, that often these update operators, they have the form of a regularized model training, local model training. So they often, when I see this here, so you see it already here. So this update has this form here. So we minimize the local loss function plus some regularization term. So these operators, which look quite abstract here, but in practice, you can implement them via regularized model training. And regularized model training you can do in different ways. As I said in the beginning, you can do it by adding a penalty term to your local loss function. This is easy if you use PyTorch, or you can do this regularization by adding additional data points, or by augment your data set. And you will see this in the assignment, how you can implement this update operator by doing by training a linear model using scikit-learn, but on an augmented data set. And in this augmentation, you bring in the information from the other nodes, from the models at the other nodes. Okay. Yeah, I want to also point out an extension or generalization of this algorithmic model. So in the simplest form, in the simplest setting, the federated learning algorithms, they repeat the same operator in each iteration. So in each iteration, you apply the same operator. They don't change over time. But this is somewhat restrictive for practical systems. It's already restrictive for this simple case here where you use a varying or an adaptive learning rate. So if you use a learning rate that depends on the number of iteration, then you cannot write it anymore in this form because this operator, calligraphic F, would change over time. So it's often useful to use a bit more general model for federated learning algorithms, which allows these operators to change over time or over a number of iterations. So at later iterations, you use a bit different update operators than in earlier iterations. And one reason could be, for example, when you use gradient methods, you use a decaying learning rate. That's one reason or one factor that can make this update operators depending on the iteration index t or time. You can think of this as a time, as a discrete time t. And this is also relevant. So this setting is relevant for online learning. In online learning, these operators at time t, they involve the data point, the newest data point that you read in at time t. In online learning, the data comes in sequentially over time. So at each time point, you must take into account a new data point, and this then makes this operator be slightly different in each time step. Okay, so we are now almost through. Let me conclude by reinforcing the workflow of basically of this course. So this course teaches you a specific workflow for the design and analysis of federated learning systems. And it starts from formulating whatever application you have in mind, whatever application where you have several devices that train models and should collaborate. Whenever you are at this point, you might use this workflow. And this workflow starts with first formulate this problem, write it down as an optimization problem, in particular as an instance of GTV minimization. This requires you to identify or to choose the local loss functions. You have to choose the edge set. What are the edges? You have to build a model for a real world application and then use this model to write down GTV minimization. Then the next step is to find a fixed point characterization of the GTV min solution. So once you have written down this GTV min problem, try to find an operator such that the solutions of GTV min are fixed points of that operator. When GTV min is something like a smooth convex optimization problem, one very natural choice is the zero gradient condition that maybe some of you have heard in a first class on optimization or calculus. And this zero gradient condition is one way to get such a fixed point characterization. And this fixed point characterization involves an operator that I call calligraphic F with different fancy superscripts, but it's always some calligraphic F. That shows up in this fixed point characterization. And this operator, once you have found this operator, you use it as an update, as the update rule for an iterative algorithm. And this gives you a federated learning algorithm. So a federated learning algorithm consists of iteratively applying this update operator calligraphic F. And this calligraphic F you get from the fixed point characterization of GTV min. Okay, and in the next few lectures, we discuss some of the core questions, which is where do the fixed point iterations converge to? Ideally to the solution of GTV min. So this first question is solved trivially or answered trivially when you use an operator that appears in the fixed point characterization. But for some reason, you might not be able to use exactly this operator because it's difficult to implement it in real hardware. So you use a bit of a perturbation. So what's the effect of perturbations in these iterations? This is related also to the statistical properties. And then, of course, how do you implement this fixed point iteration in practice? That is, over a network of devices, and this network might be small wireless battery-powered sensors that are placed all over the forests of Finland and connected by very low-rate wireless communication links. Or they are only connected by somebody reading out the memory card every 2 months, storing it on a computer. So these links or the collaboration might rely on very low rate communication links. Okay, that's all for today. And in the next lecture, next two lectures, next week, we talk about, we focus more on this design of this operator's calligraphic F. So how do we turn an optimization problem like GTV-min into a fixed point equation using some operator F? And how can we tell if this operator F is suitable for just iterating it? So that is this operator a contraction, yes or no? And you will also hear about then this, maybe one of the most beautiful results of applied mathematics, in my opinion, which is Banach's fixed point theorem, which is the precise formulation of my rule of thumb that when you have a nice operator that is a contraction, just iterate it and you will get the solution. Okay, thanks a lot for your attention and please post your questions on the chat. So there is a question, how does GTV-min take into account the discrepancies between nodes exactly if it gives us the optimal weights? Yeah, it gives us the optimal weights. The optimal weights in terms of GTV-min are not the weights that minimize the local loss function. So when you look at this optimality condition, when you have a solution, then this solution, this optimal choice of hypothesis must somehow balance this local loss function and the influence from the others. So you can also read from this optimality condition here, you see this is like an ensemble effect. So the solution at node I cannot be the solution that you would get from just minimizing the local loss function, but it must balance the local loss function minimum with those you get from the neighbors. So this is some kind of averaging that you will implement here in this optimality condition. So when I say optimal local weights, then I mean the solution of GTV-min, of the solution of this coupled training problem. Next question. How can we obtain the most optimal values for the discrepancies and the edge weights of the network? Very good question. So in this course, we assume that the network structure and the edge weights are given. So this is a design choice that somebody has already made for us. But in practice, or in many applications, or in some applications, you would need to determine if you should collaborate, yes or no, and to what extent. And as I mentioned already before, one way could be you share the simple statistical properties, simple statistics about your local data sets, like the mean and the variance. So this red node here sends its local mean and this sample mean and sample variance to the blue node, and the blue node does the same in the other direction. And if they find that they are sufficiently close, they say, okay, it seems like we could have similar statistics or data statistics. So let's try to collaborate. And then if you collaborate, you could then afterwards see if it decreased your validation error or tested error. So, but this is beyond the scope of this course. We have some current research topic in our group which studies optimal methods to test if you should collaborate, yes or no. So you can formulate this as a hypothesis testing problem. But within this course, we generally assume that some guru told us, use this federated learning network with this edge weights. Then another question, is page 31 an example of using gradient descent for squared L2 norm? Page 31, let me find it. Page 31. Yes, this is a special case of GTV-min when we use smooth and convex local loss functions. For example, like in linear least squares regression, or squared error loss is smooth and convex, and we use squared Euclidean norm for the discrepancy measures. Then we can use a zero gradient condition. if we would use here the Euclidean norm and not the squared Euclidean norm, this would not work anymore because then we cannot compute the gradient for every point. So, or if this loss function here would be the absolute error loss, which also results in a non-smooth loss functions, or it would be non-convex. Then the zero gradient condition is not sufficient for optimality. Yeah, so this slide 31 studies a very narrow special case of GTV min. Okay, any other questions or comments? Yeah, it was quite a lot of substance today, so let it sink in, and we'll put the recording soon again on YouTube. And I had a bit of revision in the slides, so we'll update the slides on GitHub, and we will now open quiz 2, which tests the lecture today, what we talked about today, and your solution for the coding assignment, which is specified in the PDF A2. Okay, thanks for your attention and have a nice evening.